day 3, arguably the most important day. It's the day, applications day of this Computational Challenges workshop. And to start off, we have a tutorial by Katherine from Duke University, who's worked on many aspects of applying statistics and Bayesian methods to data sets of different types. Today, it will be machine learning for healthcare.
Okay, so I'm going to try to talk about machine learning in the healthcare setting. So I think in this workshop, we've heard a lot about different inference techniques and like how to scale up doing inference in various settings. And like this is really to bring home kind of like why that's important, right? Like why is it that we're interested in learning about complex data and doing inference on lots of data to begin with. And so the first thing I should say is I'm really not going to cover all of the machine learning and healthcare work there is out there. There's less probably than there should be, but like there's really awesome work by people that I'm really not going to even mention. So like Dave and Rajesh have like a bunch of like really super awesome work. David Sontag, you know, like just a whole bunch of people. I'm going to talk really about the work that I've done because that's really what I know most about, and the sort of the work that's led up to those particular lines of work. Okay, so this is my outline. So I'm going to start by talking about some of the electronic health records based stuff that we've done at Duke. It's a lot of time series modeling, a lot of Gaussian process-based models for looking at chronic kidney disease and looking at sepsis. I'm going to talk a little bit about surgery. We've been collaborating with some people in surgery off of data, which is part of like this national database called the National Surgical Quality Improvement Program. And we've done a whole bunch of things to try to predict surgical complications in that setting. And then the last thing I'm going to talk about, which is something that I'm super interested in, is mobile apps in general for looking at healthcare data. So we've done a project which involves modeling kind of like the spread of infection or influenza within student dorm social networks. But we're also in the process of building mobile apps for some chronic diseases like multiple sclerosis. I'm really interested in kind of like how you look at different sensors, like newer, if you can call mobile phones newer technology, and looking at how you can integrate them into the healthcare system, and then what kind of challenges they provide from a machine learning kind of inference standpoint. Okay, so I'm going to start by talking about our work in chronic kidney disease. And as a motivating example, this is a patient who was seen at Duke. eGFR, which is on the y-axis, is a measure of how well your kidneys are functioning. It's basically a linear equation that people have come up with. So GFR is glomerular filtration rate, and they can't actually measure your GFR directly. It's a very invasive procedure in terms of your kidneys, and they don't want to do that with every patient, but they want to get a sense of how well your kidneys are working. So what they do is they come up with this eGFR, or estimated glomerular filtration rate. And they calculate this by looking at a particular lab value, mostly called creatinine, and some other things. Okay, so on the y-axis is eGFR, basically a measure of how well this person's kidneys are working, and on the x-axis is their age. And you're going to see all of these things on this chart. Okay, so at age 47, this patient presents themselves to Duke. They have untreated diabetes, they have high blood pressure, their kidneys are functioning normally, but like there's a little bit of evidence that something is happening, and the person isn't receiving regular medical care. At age 49, 2 years later, their kidney functioning is now 50% of what it should be. At age 51, so this is 2 years after that, their kidney function is now under 20%, and for the first time they're referred to a kidney specialist, right? So basically your kidneys have can be functioning at 20% of what they're supposed to be before you'll even get the referral to nephrology. 3 months later, the person presents to the emergency room with kidney failure and crash starts dialysis. So why is this bad? This is bad because you need emergency dialysis, and so people have to put all kinds of lines in your body which come with high risks of infection and other things. And it's also an incredibly expensive procedure from the hospital standpoint. It's one of the most expensive procedures, single procedures a person can have. So they continue on dialysis for the next 10 years before they pass away, and obviously this is a person with lots of problems. But this period of time right here, the first few years, is a period of missed opportunities, right? We had the chance to prevent or delay kidney failure in this individual, and that wasn't acted on, it wasn't even noticed. And we had a chance to prepare for kidney failure, which was sort of imminently coming down the line. And the way that you do this is like you pre-insert like particular lines and things like that, so that you're in a much less risky situation. Okay, so 42% of people start dialysis having no prior nephrology care. So that means that their kidneys have totally failed and they've never even seen a kidney specialist. And less than 10% of people with moderate chronic kidney disease even know that they have it. And less than 50% of people with severe chronic kidney disease even know that they have it. And so this is a problem, and this is something that we'd like to try to address. And one of the ways that we'd like to try to address it is by looking at things like, what is your EGFR? What are your lab values? So in the long run, I would like to even get rid of EGFR. It's an estimated really crappy linear equation, and you can probably do better just by looking at creatinine and other lab values individually. But we'd like to be able to use these measurements in order to be able to create machine learning methods which are able to predict what's going to happen to somebody in the future, whether they're likely to suffer from kidney failure, et cetera. Okay, so this is where I transition to talking about our work and how we made an attempt to do that, yeah.
If the EGFR was so low, apparently they did take some blood tests.
Yeah, creatinine is a blood test.
Looked at the blood test, was just ignoring it?
Yeah, so let me go back to this chart. Yeah, so see this dashed line at 30? That's a threshold, right? So that's when you're first referred, that's when medicine says to first refer you to a kidney specialist. At 15, there should be another dashed line. That's when medicine says to start you on dialysis. While you're up here, this whole range, you can be tanking like what you see. Nobody's paying attention because you haven't crossed that 30% threshold. Okay. So what we want to do is basically we want to be able to look at a bunch of things like lab values and be able to predict from this whether somebody is at risk for severe chronic kidney disease in the future. And so fortunately, a nice model for basically a single trajectory, so you can think of a single lab value, was given in the Shulam and Saria paper that was published at NIPS in 2015. And this is basically, as you can imagine, a model that makes sense for a single time series trajectory, and it's a Gaussian process model. And the Gaussian process model has sort of a complicated mean function where it's looking at sort of a population effect, taking into account people's individual covariates, their demographics, things like that. It's got a latent subpopulation curve, so we're going to say that the pool of people with chronic kidney disease can be broken up into many different kinds of subpopulations, and you belong to one of them, and so your curve is likely to look like this, right? It's likely to go down and then up, it's likely to tank, it's likely to whatever, right? So you're assigned to one of these subpopulations, and there's a subpopulation effect on your curve. And then there's your individual long-term deviation. So like you as a unique individual, how do you deviate from your subpopulation? And then look at sort of the variance of individual transient effects through a standard kernel. And so that was a really nice paper, and we decided to take that kind of approach and look at, it was applied to modeling like scleroderma. It was applied to modeling a particular autoimmune disease. And we decided to look at it for chronic kidney disease. And the thing with chronic kidney disease is that, so first off, there are a whole bunch of labs, right? So you need kind of like a multivariate version, right? So we looked at sort of a factorized multivariate version across a whole bunch of different labs. We looked at this Gaussian process model that I just described, and we said, okay, well, what we really think is going on is that people are having some kind of problem, right? So there's like an underlying physical issue that somebody is having, right? And so what we really want to do is we want to look at the trajectories of all of these different labs and try to correlate them. And we try to correlate them in a couple of ways. We try to correlate them through the long-term deviations with a multivariate normal. And we also try to correlate them through subtype assignments, right? So we say you as an individual belong to a particular subtype, probably, or you have a distribution over subtypes. And we think that your subtype is going to be fairly consistent between different lab measurements. And we do that through a mixture of multivariate normals. OK, so we look at 6 variables of interest, the EGFR, which I talked about, 5 other labs that are related to chronic kidney disease. We look at a cohort of 44,000 patients at Duke with at least moderate chronic kidney disease, and a whole bunch of measurements. Basically, again, this is the creatinine lab value. So basically, our goal is for each test patient, we're going to use data earlier in time to be able to try to predict what future lab values are going to look like. And then for each lab, we're looking at what the mean average error is across test patients. And we're going to compare it to the sort of totally non-correlated baseline Gaussian process version. And basically, this is just to show, this is a table from our paper, which basically shows that for most of the lab values, we do significantly better by introducing this correlation. This shouldn't be totally surprising, right? But like when you look at different lab values and you try to correlate them with, based on sort of like saying there's something latent going on in the individual, that's a win. Another thing that we looked at was chronic kidney disease is also correlated with other things. So it's correlated or causes heart disease, right? So somebody who has chronic kidney disease could have heart attacks, they could have strokes, they often have diabetes. And so one of our goals was to be able to model jointly chronic kidney disease in the form of estimated EGFR with these events, these bad events, right? Like heart attacks, strokes, et cetera, et cetera. So our goal here was to come up with a joint model of loss of kidney function and cardiac or stroke events. And so basically, we did this through a hierarchical latent variable model that captured dependencies between the disease trajectory as given by EGFR and the point events that, that we captured through some kind of event risk. And we came up with a basically a conditionally independent joint likelihood model, right? So here is the model for EGFR, which is the model that we talked about previously, and here is the model for the events that we're looking at, like heart attacks or strokes. Okay, and like I said, we talked previously, it's the Gaussian process model for EGFR and the trajectory of how somebody's kidney functioning is doing. But in terms of getting the joint model with the risk of heart attacks or strokes, we're going to look at a pretty straightforward point process model, a Poisson process model with a conditional likelihood on events. Or we're going to use a rate function, just the hazard function, and a Cox proportional hazard model. And so the idea here is that when we look at the rate of events, we're taking in information from the time series model, the EGFR time series model that we were talking about learning previously, right? So we look at its mean, and we look at the standard deviation, basically, and we take that into account when we're looking at the rate of actually having these events. So we're tying the two together in that way. Okay, and so when we went to look at the joint model, can we jointly model sort of somebody's chronic kidney disease trajectory with like their risk of heart attacks or strokes? We looked at 23,450 patients at Duke with moderate stage chronic kidney disease and more than 10 EGFR readings. Right here. Okay, sorry. And so we also looked at people who had basically this is stroke and this is heart attacks associated with their chronic kidney disease cases. So about 13.4% had a stroke and 17.4% had a heart attack. And what we get is something like this, right? Something where we can say, this is our mean function of what we think that your kidney functioning is going to look like over time. And we can also, at the same time, come up with a computed risk of having any one of these other adverse events like heart attacks, right? So here, basically what we're doing is we're moving forward in time based on and so we're conditioning on everything to the left, and we're predicting everything to the right, right? So as we move forward in time, we get a better and better sense of exactly what the trajectory looks like, but we're doing a pretty good job of prediction. And as you can see, once somebody has had one event, their likelihood of having more goes up dramatically. So this is most of what I have to say about, about our work on chronic kidney disease. This was published at UAI and MLHC, the Machine Learning and Healthcare meeting. And basically, this kind of thing has been incorporated into various kinds of rounding tools at Duke, and we've rounded with it a little bit. You'll find, like everything else in medicine, there's a lot of red tape and bureaucracy in terms of getting these into sort of the daily care of patients. And I'll talk about more projects where we've been slightly more successful at doing that. It's interesting because they're very keen to move to something that's slightly more data-based, but I think in terms of things like this, they don't know exactly quite what to make of it. And so one of the things that I'll definitely support is working with somebody in user interfaces in order to be able to come up with a good interface for clinicians.
So moving beyond just observing things, there's sort of the causal question of how do things change when you actually intervene. Have you thought about that?
Yeah. I'll talk about that a little bit. So not much, right? Because it's a little bit farther down the road from where we're at right now. But I think it's a very good, very important question. And so I've got a graduate student who's very interested in sort of causal inference. What can we say about the causality of the intervention on the change trajectory of the patient? Yeah, no, that's really good. I'll mention it a little bit going forward.
Katherine, can I ask a related question? Are there interventions in these patients that you are analyzing?
No.
So they're all?
Yeah, no. So straight up, most of the work that I'm going to present here is really straight up prediction. It's data pulled from the electronic health record system. We don't really have the ability to say, based on what we're doing, go back and...
Were there treatments? Did doctors do things to these patients in terms of you're forming a prediction based on the idea that they're going to march through life with the same kind of rate of treatment that they had before?
Yeah, the answer is obviously yes, but it's not something that we've tended to look at, right? How does starting somebody on a course of antibiotics at this point actually change their trajectory? What we'd like to do, I think, in the final analysis, we're starting to round with patients based on these methods, is to look at evaluating how much presenting this kind of information to providers makes a difference, and then how whether or not their treatment of patients is affected by kind of what they're seeing and how much impact that actually has. Yeah. Okay. So the next thing that I'm going to talk about is sepsis and sepsis prediction. This is, again, another thing that the hospital is very interested in because a lot of money goes into dealing with patients who have contracted sepsis. So sepsis is basically an infection that you contract usually in the hospital because through some line or something that's been put in. And it's very life-threatening. I think 50 people who have serious sepsis basically end up dying from it. Okay, so what they use right now at Duke is something called NEWS, and NEWS is shown here in this chart. So basically, if you're normal, all of your vitals are in the ranges that are shown here, and as they get worse and worse, basically you move from having 0 points to having 3 points on either extreme. And you add it up for every row, right? So it's if your respiration rate is less than 8, that's 3 points. If your oxygen saturation is between 92 and 93, that's 2 points, so for a total of 5 points, that kind of thing. And so again, like this is what they're currently using, and this is like a very, very simplistic kind of threshold-based method. I mean, so you'll get the impression time and again that what's currently being used in hospitals is very sort of like thresholdy, very kind of rule-based, right? And so one of our goals is really to see like, can we move away from that to a more into a more probabilistic setting and do better? And the answer is almost always yes, right? Okay, and so there's been a bunch of work on sepsis. Suchi and company had a paper in Science Translational Medicine, which basically just uses a straight up Cox regression in order to predict septic shock. There were some weirdnesses with the time series aspect of that. And so what we really wanted to do, like if you notice this, like there's really no temporal component, is to introduce a temporal component into this kind of sepsis prediction. And so again, we're going to fall back sort of like on GP regression in order to get a complete time series, right? So we're interested in being able to classify time series with sparse and irregular sampling on some kind of common time interval, 0 to t. And so what we have are observation times t. These are like when labs are taken. Some observation values b. These are like the values of the labs. And some reference times x. So you need a way of relating one time series to another, right? Which means that you have to look at the latent function at the same, basically at the same time, right? And that might not be the time when the lab is taken between people. Okay. So we're going to represent a particular time series by its marginal posterior at x, at a reference time x. And so basically we're going to use Gaussian process regression, this is the original Marlin NIPS 2016 paper. They use a Gaussian process regression with zero mean and some set of parameters, the kernel parameters and noise parameters. And so so your predicted function is random. So you can use an expected loss with respect to a Gaussian process posterior, right? So you have, basically the idea is you have this function for like lab values over time, and what you want at the end is like a classification system. Is this person likely to have sepsis or not have sepsis? And so the idea is that you take the output from what you expect this person's trajectory to be like in terms of their lab values, and you feed it into a classification system. And basically you try to classify, like, is this person at high risk or not for sepsis through the classifier. Okay, so GP, then classifier. Okay, so we're going to learn the Gaussian process parameters and classifier parameters end to end using this particular loss function. So we're going to look at minimizing the expected loss with respect to the Gaussian process parameters and the parameters of our classifier, where the loss is given by the function value, so like the lab value going forward, combined with the classifier, then fed into the classifier, right? So do we have the right label or not? And so in order to calculate this, basically we need to be able to take gradients of this expectation, right? And basically we use the same reparameterization trick that they use in, say, like Kingma and Welling, right, for VAEs, in order to translate gradients of an expectation into expectation of a gradient. And then we approximate the intractable expectation with a few Monte Carlo samples, and then we use other things in order to speed up this kind of optimization inference, right? So conjugate gradients to compute the GP means and covariances and the Langsos method in order to efficiently draw samples from the GP. And then we can do backprop in order to do end-to-end learning through a classifier, a GP combined with a classifier, yeah.
So the predictions here are lab values.
The predictions is like, does this person have sepsis or not? Is this person at risk of having sepsis or not?
I mean the sort of the disease.
Yes. Yeah. So the disease is captured by lab values and vitals, right? So sorry. So what I showed here in the chart, all of these things, all of these vitals, things that will be fed in terms of like, this is a time series that we're going to look at that we think is related to predicting whether or not you have sepsis. And then we're going to feed other things into the classifier as well, like when was the last time this particular measurement was looked at, because that's important also. But the main thing that we're going to feed into the classifier is this function value. Okay, so what we do is, again, we have a similar setup, but we now have a multivariate time series. So we have a time series basically for each one of those vitals, each one of the lab values that got taken. These are highly variable in length. A bunch are less than 12 hours long. Some are more than 10 days long. And so what we want to do is we want to be able to use this clinical time series, baseline covariates, times of medications that were given to patients in order to be able to predict, does this person have sepsis or not have sepsis. And so instead of having a zero mean function, we have a mean function which depends on like the medications that are given to the patient, right? So we look at sort of, this is like an exponential decay on, was this medication given sort of recently? If so, this is going to play a lot into the mean function. Yeah.
What happens if some patients, some of the lab values are missing? Or?
Yeah. So right. So basically, basically, okay, so when we actually go to look at this group of people, right, we say everybody has at least a certain number of measurements, like in each of these things that we're looking at. When we look at like vitals, because a lot of this is actually vitals based for sepsis, right, we're looking at a situation in which vitals are taken constantly, basically for anybody who's admitted to the hospital. And so that's one of the nice things about this. Again, if I go back to like this new score, I mean, you can calculate this new score. I think it's like once every 6 minutes, in theory. Okay, so I'll get to that on the next slide. So we also redesigned our GP kernel function in order to look at sort of like covariance between all of the time series as well. So we have a separable kernel, sum of separable kernels that we use, and then we use a recurrent neural net classifier. Okay, so this is like another story of another patient who came into Duke. So this one is a 37-year-old woman who came in complaining about chest pains, and this was a person with a history of hypertension and also of having a pulmonary embolism, like a clot in your lungs. And basically all of these things are things that play into the different kinds of lab values, or the values, the time series values that we look at, right? Pulse, oximetry, respiratory rate, temperature, et cetera. So again, these would be collected very frequently. And we look at how our method does in terms of predicting whether or not the patient has sepsis. And basically what we see is that this is what the predictions that we make are looking like. This with the red X is when the person actually qualifies as having sepsis by the diagnostic criterion they have laid out now. And so basically this is just an illustration of, so the person, basically this person, sorry, I didn't finish giving the story. This person, it was thought had another pulmonary embolism. They were admitted and they had basically a very invasive surgery where they basically opened up her lungs, her chest cavity, and physically removed the blood clot. And then she was admitted from surgery. She wasn't doing so well. She was admitted to the ICU. And it's unclear whether she got sepsis during surgery or in the ICU. But this is basically the kind of prediction that our method makes. Again, this is when she actually qualifies as having sepsis by medical standards. And so basically this is to illustrate that we can do a much better job of using this kind of data in order to try to make these predictions in sort of like a principled machine learning probabilistic framework. Okay, so the data that we actually looked at overall was 52,000. Was from 52,000 inpatient encounters. That's what we trained on, and then we had 14,000 inpatient encounters for testing. There were 31 longitudinal variables, 6 vitals, 25 labs, and 36 covariates, 8 medication classes, et cetera. And these were the results that we got. So basically, everything that's a solid line is our method, and the left plot is area under the ROC curve. The right plot is area under the precision recall curve. These are two different curves that try to get at both the precision and recall kind of concept a little bit differently. So we check them both, and so you can see we move from a raw RNN to the multitask Gaussian process RNN combination that I talked about. We look at adding the medication effect, which is the sort of the moving the mean from being mean 0 to actually depending on the medications that the person was given, et cetera. And we do better basically every time. This lab missingness indicator basically just indicates how long it's been since they were last. They had a lab last taken, because that can be very informative. It's like, oh no, don't take the person's blood pressure, you might kill them, right? Things that are not necessarily causal, as John brought up, right, can be very informative in terms of how the person is doing, a sign in terms of how the person is doing.
I don't know if I'm seeing the lines right, but it looks like news is pretty decent, except very close to sepsis. Is that right?
Yeah. So there, when you look at area under the ROC curve, right, it's doing pretty decently, right? So this is hours before a sepsis diagnosis. That's right. Why that is, I don't know. If you look at the precision recall curve, an area under the precision recall curve, it doesn't come out nearly as well, right? So this is just differences between ROC and precision recall curves. It's just, overall, it doesn't perform nearly as well at any time point, right? You can see here, but it does look that way there. And so one of our goals is to put this kind of into a web app that people can use sort of in clinical encounters, where people who are at high risk for sepsis can be flagged as potentially being at high risk for sepsis. And then you'll see this theme kind of running through a lot of the work that I'm talking about. And then different kinds of treatments or different kinds of interventions that can take place in these patients are suggested, right? So it's if you feel like somebody is at high risk of sepsis, you can send them to treatment. You can decide to start them on antibiotics. You can decide to retake a particular lab value in a certain amount of time. And those are all suggested kind of in a bundle as particular things that you might want to do. So right now, the treatment for sepsis is very sort of it's very kind of laid out, right, in the medical system. And this is not something we particularly want or have the ability to affect, aside from just showing this extra information. Okay, so I'm going to move on to the surgery domain. Are there any questions about that?
Quick question. So you have a sense of how that news chart was constructed? Was it based on a specific?
This one? Sorry.
That nice table was, or is it just experts who have a whole lot of experience kind of put together something?
This is definitely this is a rule-based thing that everybody in our hospital system uses. I expect, so that's a good question, and the answer is kind of no, right? I expect there are various boards at the AMA and they sort of like do a review of things like sepsis, and they put together sort of like these kinds of rules and charts and stuff like that for measuring different diseases, and they get handed down to the clinicians, and the clinicians just kind of like look at the rules and charts that they're handed and just kind of like check off boxes. It's kind of what's going on right now.
So even if one were to stick with, a simple structure like this, one could potentially improve it by using data, perhaps.
Yeah, potentially, right? So it's like if you want to stick to a rule-based system, and this is something that, like I've talked to you a little bit about, like not argue, but like I discussed with people at Duke a fair amount, right? Like, so one of the things you want to do, one of the nice things about this is it's incredibly interpretable, right? Like, you understand what blood pressure less than 90 means, right? Whereas for sepsis, this is less true for some of the other stuff that I'm going to present. But for sepsis, like our method right now is incredibly uninterpretable, right? So you're getting a predictive score out. It's saying, okay, you have like a 95% chance of having sepsis or whatever, but it's not clear why it's saying that, right? You have like a GP regression feeding into like an RNN classifier, like who knows? I mean, this is an issue that's been brought up a lot over the course of time that people have been presenting here. Who knows exactly what's going on? Whereas this is a very interpretable kind of graph. Can we improve on this? Possibly. But I don't know, because that's not been what I've been trying to do. But I do definitely have an interest in taking the kind of like GP-RNN classifier framework that we've been developing here and making that more interpretable. So you can feed back to clinicians, this is exactly why it is that this patient is being flagged for having sepsis. Here's what you might want to do about this particular feature. And I'll talk about this a little bit more in surgery, because we have a better sense of exactly what features it is that are playing into somebody having a risk of surgical complication. Okay. So this is a system we've been working on for predicting surgical complications in patients going into surgery. So there are lots of different kinds of surgery, and basically I think 12 different kinds of surgical complications that we look at, pulmonary complications, bleeding complications, et cetera. So about 15 out of every 100 surgical procedures results in some kind of complication. And in 2014, which is the last year that we actually have numbers on, Duke spent more than $9 million in treating postoperative complications, right? And so you can see a few of the different kinds of postoperative complications that somebody can get listed there. And so the data that we actually use to address this problem, so I had talked in the beginning about data that was pulled from our electronic health record system. And the data that we have here is actually, in a sense, it's better. It's called NSQIP data. And the NSQIP stands for the National Surgical Quality Improvement Program. And so the idea is that there are certain variables that all of the hospitals, not necessarily all the hospitals, but all the hospitals who belong to NSQIP kind of like feed into this database. So you have a lot of data coming from a lot of different hospitals. It's anonymized in the sense that we can't figure out, unfortunately, what hospital is providing what data. We know what data we provide, but we know what data we provide to the NSQIP program. And this is just a figure saying, okay, somebody had, in 2016, somebody had a JAMA article. So this is the Journal of the American Medical Association. So this is like one of the most high-profile medical journals around, basically showing like, oh, like just belonging to the NSQIP program doesn't actually make your outcomes any better. And it's like, yeah, well, you have to actually take the NSQIP data and like use it for something that's going to affect your outcomes, right? But this is apparently kind of news to them. So it got like a JAMA article publication. But yes, so one of our goals is to actually take this data, take the NSQIP data, and use it for something which is going to help improve outcomes for patients. Okay, sorry. Okay, and so kind of the first line thing that we tried was just a sparse logistic regression model. So we have a whole bunch of variables. The variables, well, you'll see some of them on the next slide. The variables, there are a lot of procedural codes. There are a lot of things like how long were you in surgery for, et cetera, et cetera. And then we can look at all of sort of like the complications that you can get coming out of surgery, and we can look at the area under the ROC curve, for example, and we can actually notice that there's a fair amount of signal there. So if you look at like this national database, you can actually do a pretty decent job of predicting whether or not somebody is at risk for having one of these surgical complications. So the method that they use right now for determining whether or not somebody should go into surgery is by looking at the patient and going, I think you're good, like you should go in, right? And so this is literally what we're comparing to, right? We're saying, okay, can we take like even just like a very simple model, like a sparse logistic regression model, and do better than a surgeon walking in to somebody's room and being like, you look like you can make it through surgery to me, it looks good, let's go. And so here's the larger amount of interpretability, because logistic regression is a highly interpretable method, right? We can look at what variables are being weighted highly, what variables are actually playing into your chance of dying or your chance of having some kind of surgical complication. And basically one of the things that we can notice is that there are some things that we really can't do very much about. So you're diagnosed with esophageal cancer. We probably really can't do very much about that, right? Like that is just the situation that you're in. You're diagnosed with having a nutritional deficiency. That might be something that we can do something about, right? We can call in a nutritional consult. We can try to improve your nutritional situation before you actually go into surgery, right? And so it's these kinds of interventions that we're interested in using this kind of tool to start employing with patients and seeing if they have an effect. We haven't really gotten there yet.
And these risk increase numbers, these are over sort of a baseline of not having any of these.
Yes.
Features, right? That's sort
Yes.
of like compared to the old 0 rates.
Yes. Okay. So, and I mean, again, what we'd like in the long run is for physicians to be able to have a tool that they round with patients who are about to go into surgery on. I'd actually like to see, kind of like my vision for the future is to see this prediction system which runs from their first visit to basically their last visit and predicts out to time after that. They're very interested in like whether they're likely to have problems within the first 30 days, because of course like they get dinged if somebody comes back and like gets readmitted within 30 days after like they're admitted for a procedure. I'm not personally so interested in that. I'm just like more interested in what's going on with like the health of people. But in terms of like what a hospital will pay for, that's definitely a factor. So we'd like in the end to have physicians rounding with this kind of tool which tells them about the different risks that their different patients might have and gives them options for what they might want to do about it. Right now, all the potential interventions are being suggested by clinicians in terms of like what they would do to a patient if a patient is at risk for a particular kind of complication. And so here's an example of an app that we have. This is currently a functioning app that people are rounding with in surgery right now at Duke. It's fake data. All of this is fake data for like HIPAA reasons and stuff like that. We can't actually give out real data. But so this is the name of the patient. This is the procedure the patient is having. So like a Whipple procedure is a surgery where they cut off part of your pancreas and remove your gallbladder and stuff. I won't go into the details, but this gives the risk, the absolute risk of somebody having this particular kind of complication, a wound complication, a septic complication, a neurological complication, et cetera. And then they say what percentile they're in terms of like compared to the actual population. And we've had it in the past so that you can actually pull up and see the entire distribution of people who get surgeries at Duke and like where that particular patient is falling. And then in terms of their interventions, they're listed here. So a doctor can check off, say, like the septic bundle, and then get a whole bunch of options for what kinds of interventions they might want to take, given that this patient is at high risk for a septic complication. Again, these intervention suggestions are given by doctors. So here's an example. This is the wound bundle, right? So you're looking at right here, because this is more interpretable, this shows basically the kind of risk factors that are going into this person having an increased probability of having this kind of complication, but then also sort of like a whole bunch of common interventions that you might want to take if you feel like people are at risk for this complication. Okay, so we've also tried to do some more methodologically interesting things with this data. So one of the things that this logistic regression runs off of is the clustering of procedural codes. And the clustering of procedural codes right now is done by hand. It's just like a group of clinicians have looked at it and said, okay, I think these procedural codes go together. And this is what we've been using with our logistic regression system. And so one of the things that we've been interested in is, can we use a clustering kind of methodology like a hierarchical clustering kind of methodology in order to say, okay, these are the procedural codes that go together if we want to maximize our ability to predict whether or not somebody is going to have a complication. So we're looking at merging procedural codes together, and we're merging them together basically based on what's going to increase our ability to predict surgical complications the most. And so doing clustering of procedural codes in this way leads to a modest improvement of 7 out of the 8 outcomes. Another thing that we've been looking at is transfer learning, right? So we have this National Surgical Quality Improvement National Database for surgery. We also know what data our local institution is contributing. That's Duke University. And so the idea is that the patients that are seen at Duke are probably not exactly represented in the national database, right? Like the population of people that Duke sees is going to be slightly different from the population of people who are seen on a national level across all hospitals. And so I have a student who's worked a little bit on a hierarchical infinite factor model for looking at doing transfer learning between the national data to the local data. So basically saying like, okay, can I downweight the national data a little bit and upweight the local data a little bit so that the national data is giving me information in places where I feel like it counts, right? And so the idea is sort of think of normal factor analysis. The factor loadings matrix is chosen in a way that you have a stick breaking prior and you're just choosing particular factors that are found overall in the national database for like the Duke data. And you could also apply this to other hospitals, right, which would have its own subset of factors. But we don't have that data. Okay, and so what we found is that doing this, the hierarchical infinite factor model, improves our ability to make predictions about these surgical complications, right? Doing this kind of transfer learning improves our ability to make predictions about surgical complications off of just looking at the national data alone. One of the downsides of this, that we've been working on the hierarchical infinite factor model, is that right now it's just using some standard sampling methods, right, like Gibbs sampling, and is not like that fast. So this database, this national database, has about 1 million people in it, and there are 500,000 people who have, data of the kind of quality that we would be interested in using. But like our methods can really only handle up to 100,000 people right now. And so we're looking at speeding this up using like stochastic gradient nose Hoover. Am I pronouncing that correct? Yeah,
So
thermostat sampling.
The hierarchical aspect, is that basically dealing with geography? So I didn't quite follow what the hierarchy.
Sorry. So the hierarchy is, okay, so the hierarchy is like you have these latent factors, right? And then you're going to say at each institution, at each individual hospital, you're pulling from a subset of these factors, right? So if you look across all hospitals, you see like a whole bunch of factors being used, but at your individual institution, you say you only have like a subset of these factors which are playing into the data that you're observing, right? So the stick breaking prior is just allowing you to have a varying number of these factors, right? But you're saying, yeah, for each local institution, and it would apply, right? So if you were looking at like UCSD or something like that, you would have a different subset of factors than we would have at Duke, right? But you could still use the same model. Unfortunately, we have a hard time testing it because we don't actually have the individual data like from UCSD, right? Like people are kind of limited a bit to their own institution, right? We know what data our own institution contributes. The frustrating thing is like NSQIP, the National Surgical Quality Improvement Program, does actually have that information, and they have actually published on it, but they won't like give it to us, right? So this is kind of like one of the frustrations that you face, I feel like, when you're dealing kind of like in the medical realm, right? People are very proprietary about things. People reference HIPAA a lot as reasons to not share with you, basically. Okay, so, and then I talked a little bit about, okay, everything that I talked about so far was kind of postoperative. There aren't a lot of postoperative variables. We do look at sort of how long the surgery took and stuff like that, and that's postoperative. But my goal is really to create this prediction model that runs from the person's first visit through the person's last visit and runs in real time through the person having surgery, right? And we're kind of slowly making our way there. And so right now we're starting to work on the preoperative end. And that's nice in a sense because you have like more leeway for interventions, right, that you can evaluate. And so one of the things that they definitely do is they segregate people into different kinds of consults based on whether they think that they're at high risk or not, right? So if they think that you're at low risk before surgery, you'll have like a phone screen where they just give you some information, right? But if they think that you're at high risk, they'll refer you to like one of these clinics depending on your age. And so one of the things that we've definitely been thinking about doing is evaluating how much impact those different screens have on how likely somebody is to have a particular complication coming out. And you could think that doesn't really have a lot of effect on people's complications, but people's behavior can vary quite a lot depending on exactly what they're told and what information they're given during these screens, right? In terms of how like they take care of themselves coming out of surgery and stuff like that. And then there are other interventions after those screens as well that we're interested in evaluating. So that's kind of where we stand at this point. So going back to John's question, like, yes, we are very aware and very interested in doing that evaluation. No, we are not quite there yet. Okay. So how am I doing on time?
5-6 minutes.
Okay. So I'm just going to very, very quickly talk about the last kind of bullet point that I had in my outline. And the last bullet point that I had in my outline was looking at like mobile apps and their use in terms of incorporating them into the hospital system as extra sensors for better data collection for various things. And so the first thing is the spread of infection. And so I was loosely involved in a couple of studies. The first at MIT, the second at the University of Washington, basically where students in a student dorm were given mobile phones and like how sick they were and who they were interacting with was tracked. And this is kind of like a dynamic network kind of model. Where we looked at, can we predict somebody's likelihood of getting sick or contracting influenza based on who they were interacting with and their symptoms, right? So we developed something, I'm trying to see if there's anything important here, no? Okay, this is like the social network of a particular student dorm at MIT. And they reported symptoms like runny nose, nausea, vomiting, et cetera, et cetera. And so the thing that we looked at using was a graph-coupled hidden Markov model. And what a graph-coupled hidden Markov model is you take an HMM chain and you associate it with every person in your network, right? So you have these latent states, which are going to reflect the person being sick or healthy. You have their reported symptoms. Those are your observed variables. You take the chain and you associate each chain with each person in your network, and you look at them interacting over time. And so whether a person is sick or healthy in the future depends not only on whether they were sick or healthy at the previous time step, but whether they interacted with people who are sick or healthy, right? So you could imagine that if you've interacted a lot with sick people, your chances of having contracted an illness like the flu goes up dramatically. And this is basically to say inference in a coupled HMM is very hard. So it's like if it's fully coupled, if you have a fully connected, yeah.
For the previous one, where does the interaction network really come from?
It's tracked. It's tracked. It's given. So like one of the interesting things you could think about in terms of future work is like, can we predict it if you've got like 10% of your links missing? And probably the answer is yes. We've never tried to do that, right? But yes, we're conditioning on that. Like we get that data from mobile phone and Bluetooth devices.
Except for the point that actually the true number of nodes that define the network is also an unknown here.
Yeah.
For the DOM, yes, it is known, but the interaction, the true number of actual nodes in the network is also an unknown.
Yeah, no, that's right. So we have parameters. Well, okay, 1 second. Okay, so inference in this model can be very difficult, right? If it's like fully connected, like there's no good way of doing inference. So basically, we rely on the fact that this is actually very sparse. Your chance of meeting somebody else is very small. And also, we end up piping through a very small number of parameters. And these parameters are kind of the parameters that I wanted to talk about with you, because there's a recovery parameter. And there's like a did I get infected by somebody else in my social network kind of parameter. But then there's also like, did I get infected by somebody outside the network? Because there's always a chance of that. So we're trying to look at sort of like as tight a network as we can. When we look at student dorms, you know, in terms of people who are going to interact with each other instead of other people as much as possible, that's pretty much as good as we can get. But that, no, that's certainly like an issue. And so what we're comparing to here is really like standard epidemiological models, which just look sort of at a population level and say, okay, you know, half of my population is sick. What do I think, given the recovery rate, given the infection rate, what do I think my population is going to look like sort of in the next time step, right? So it's not doing any kind of individual level prediction where you're looking at sort of like who people are interacting with, and that's really what we were going after here. Can we do this kind of individual level prediction? Okay, so this is a heat map. So on the x-axis is time, on the y-axis is students. And so the black dots reflect how many symptoms the student is reporting on that day. And then the heat map reflects the predictions that our model is making. And there is no ground truth for this one. But hopefully you can see that like our predictions of illness line up pretty well with the black dots. One of the things that happens when somebody becomes sick is they stop filling out their surveys, right? Like it makes sense, I'm sick. But like I'm not going to fill out my surveys anymore, right? And when that happens, what you get are like these empty boxes. The person didn't fill out their surveys that day. And so our algorithm is like also able to infer that the person is still sick even though they're not filling out their survey. So something more complicated than just a reflection of the black dot is going on. That's my point. Okay, so when I looked at the University of Michigan data, it was a little bit better because Allison, who's my epidemiological collaborator, actually worked for the CDC for a while, and the CDC was co-funding it. And so basically, whenever somebody whenever somebody sort of like reported flu symptoms, the CDC swooped in and swabbed their mouth and their nose and stuff like that. So we know exactly what people had. Like, what type of flu did you have? Like, what type of disease? So there's ground truth for that. We looked at the hierarchical case in this case. So we were saying, okay, individual students have covariates, sleeping, drinking, smoking, hand washing, et cetera, that we think affects their rates of recovery or getting infected. And we're going to look for ways of incorporating sort of like the individual level covariates that students have into this model. And these are the results that we got. I mean, so basically just saying, now we have ground truth and we can compute precision and recall and see that we're doing a pretty good job of like being able to predict who's sick and who's not sick. And we can also see things that see like sleep quality and alcohol use is playing into people having a longer recovery time and being more likely to be infected. And these are just sort of pictures of the graph and the graph over time. As you can see, it's really sparse. I wanted to, so in terms of inference, because this is an inference-based workshop, we did a lot of Gibbs-EM work that is not super fast, but we've got a couple of papers, follow-up papers to this work, basically using stochastic variational Bayes. There's a lot of use of stochastic variational Bayes in order to try to do larger scale kind of inference in a lot of these models. Okay, and then the last thing I wanted to talk about really briefly, you put in interesting transitions. Okay, was, so there's no machine learning here, but I just wanted to mention it because we're about to release this app in a month, and hopefully we'll do really cool machine learning and learn a lot about the disease, but something like this should be happening for every chronic illness out there. So the idea is that we're looking at multiple sclerosis patients. They have a lot of different symptoms and a lot of stuff is going on, and we don't know anything about it because no data is actually being collected in clinic, even in clinic in the once every 3 or 4 month kind of outpatient visits right now. It's a very complicated disease, and so we asked, how can we monitor this more continuously in order to start making better sense of what's actually going on? And so what we did is we developed an app, and the app has lots of things that hopefully will make it a good mechanism for collecting information about this particular chronic illness. So it's got an embedded consent process, disease history surveys, various surveys about like what your symptoms are like and what your medication use is like. And different kinds of activities. So there's like a finger tapping activity, there's like a spatial memory kind of activity, there's like a can you do serial addition well kind of activity. If anybody's interested, I can show you on my phone. There's a pairing basically through HealthKit with your like fitness tracker, or just using your phone as your fitness tracker to incorporate information about like the number of steps that you're taking, your sleep quality, et cetera, et cetera. This is all coming in as data. We're trying to make it really low work for the person who's using the app, right? So it's like if nothing's changed, they can just force touch their notification and say nothing's changed, and it'll repopulate automatically with the previous day's data. They can look at the app and see what different symptoms and task performance has been like over the course of like a month, or they can change that time period a little bit. They have a medication calendar where they can say if they missed medications. They get once a week reports about what has been their worst symptom. They have reports they can show their physician about what things have been like for them in the time period between when the physician has seen them, what symptoms they've been suffering from, et cetera, et cetera. There's like a learn more section where if they're having a problem with a particular symptom, they can go to the learn more section and figure out more about it and figure out what medications have what side effects and what they do for you. And there are a lot of places that we can go from here, right? So we can use a lot of the kind of GP models that I talked about in order to model the progression of the disease over time. We can look at subpopulations based on symptoms. So like, for example, if you're feeling fatigued, right, that could be because your disease is causing you to be fatigued. It could be because you're on a particular medication that's causing you to be fatigued. It could be because you're like depressed and that's causing you to be fatigued. And to try to separate that out is really important, and we can use some standard clustering methods and maybe more advanced clustering methods in order to try to determine that. And then again, there's this sort of perpetual issue of evaluating the causal relationship between different interventions that get taken and the effect on the longitudinal models in the clinical through clinical trials. And then the very last thing I wanted to bring up was, so in this talk, I've talked a lot about joint modeling, and so we're interested in modeling jointly the data that we collect from this app with things like MRI images, which is what your clinician collects, or omics information that we also have access to. So I'm working with like a clinician, obviously, on developing this. Okay. So I wanted to say thanks to my students. So there's Joe Futoma, and he's done a lot of the work on the sepsis and chronic kidney disease work that I've talked about. Liz has really been heading up the surgery work that I've been talking about. And Kai did a lot of work on influenza. I have not bothered any of my students yet with the last thing that I talked about because we haven't actually started doing machine learning yet. So thanks.
With the app, is there any concern about privacy?
Yeah, so I mean, there's a lot embedded in the consent process, right? So you can choose who you want to share your data with. Do you just want to share it with the researchers who are doing this study? Do you want to share it more broadly with other researchers and give us permission to give it to them? Do you want to be able to make your data publicly available? So it's like if you talk to like some of the other, I won't go into details, some of the other machine learning and healthcare researchers, right, they're like very big proponents of open data and being able to put your data online. And I think that's great, and I think that's a great way to learn more about the data. I do not pretend that I am the be-all and end-all of machine learning analysis of this data to any degree, and so I would prefer that, but that's something that somebody has to consent to. And I think a lot of people actually will consent to it. When I talk to people who are involved in like startups to reduce healthcare bills and stuff like that, they're like the vast majority of people are actually not very sensitive about their medical information as long as you're protecting them from like pre-existing conditions and stuff like that that's currently going on.
Did you need to get into IRB?
Oh my God, yes. This has been half my life over like the last year, has been submitting IRB protocols and then going through different security kinds of things at Duke about like where you store your data. And then the reason this app is not out yet is because we were contracting with IBM Watson Health Cloud to do the backend basically for data storage. And like they couldn't reach an agreement with Duke over liability and data access and stuff like that. So we had to pull out from that. And so now we're going to probably store data on like Amazon, like AWS, but Duke won't sign a contract directly with Amazon, so we have to go through a third party in order to make that happen. You have no idea. Like.
I have a little bit of an idea.
Yeah, I'm sorry.
There are some startups that do HIPAA compliant clouds on AWS, etc.
Yeah.
Because they're startups, they're much more flexible to the vagaries of universities' contractual procedures.
Yeah. And I mean, that's in effect what's going on, right? So these startups are often taking something like Amazon, they're siphoning off a piece of it. They're saying, we're going to run some extra sweeps of like HIPAA compliant protection and then sign a liability agreement that at least Duke thinks it's not going to get Amazon to sign. And that's exactly what's going on. I don't know whether that's a good or a bad thing at the end of the day. I kind of just wish Duke would sign an agreement with Amazon and call it a day, but like, yeah.
So you're sharing these predictive models with doctors. Are the doctors at all sharing them with their patients?
I mean, yeah, that's a good question. So I would say not yet, but that's definitely a goal, right? So like one of the things, so if it's like, if you're at risk for a surgical complication, that's something you should know and be able to make a decision about before saying that you consent to surgery, right? Like, it's like, if we think that you are going to be at high risk for like a bleeding complication, you should be able to evaluate whether or not you want the surgery kind of like based on that. And so that is our long-term goal, but that we are really just starting to introduce it to clinicians. So we're just too early for that, but yeah, no, I totally agree that should be happening.
So we have a break till 11.